Welcome to ECE 3300 at the University of Utah. In lecture number 13, we're going to be talking about impedance matching. The idea of impedance matching is to be able to connect something like an antenna or another kind of load that might not be 50 ohms. We want to be able to connect that to a 50 ohm generator or a 50 ohm transmission line and not have any reflections, and therefore we want to do an impedance matching circuit. The first thing that we're going to learn is how to add parallel or series lumped elements to a circuit. Sometimes this is done for matching, but it can also be done for other reasons. We also are going to learn to use single stubs to match our circuits. The stubs could be either series or parallel, open or short-circuited. Sometimes single stub matching is called distributed matching or matching with distributed elements. We also are going to learn how to match a complex load with a quarter wave transformer. So here's the idea of single stub matching networks. If we have a transmission line, which has a characteristic impedance Z0, and a load, which is not equal to Z0, we want those to be able to be matched. So sometimes we will put just a stub in series here, get rid of this little part right there, and what we'd be looking for is the distance between the stub and the load and the length of the stub. This is shown as a short-circuited stub. We also have open-circuited stubs. And by the time we get right here to this point, the input impedance of our line should equal the characteristic impedance. This is matched. Another way to do this is to use a parallel stub. That's again where our load is not equal to our characteristic impedance, and we just put a stub in parallel. Again, we design D, and we design L, and this one is shown as an open circuit. Here's the basic idea behind stub matching. Let's consider what would happen on our Smith chart if we were right here and we said we wanted Zn to equal Z0 plus J0. If we normalized this, this would be 1 plus J0, and that's what we'd want to plot on our Smith chart. So if we were designing a series stub match like this right here, we would know that at this point we want to be a real part of 1 and an imaginary part of 0. Well, what happens when we rotate on the Smith chart a distance d? We can rotate on the Smith chart and change both the real and imaginary part. So this value changes, I'm going to use delta to mean change, the real and the imaginary part of ZL. But what about this little stub right here? This stub can either be an inductor or a capacitor, but it can't be a resistor. So the only thing that this can change is the imaginary part. So what I'm going to need to do is rotate a distance d to fix my real part. It will also change my imaginary part, and I'm going to call that ZA. That point I'm going to consistently use as ZA. And then when we add in this stub, we're going to remove the imaginary part and not change the real part, and that way we'll end up with the real part we want and also the imaginary part that we want. So there are several things that we need to learn in order to do this. One is how to add series elements. Another is what it means to rotate and design a single stub matching network. We also need to know how to make a short-circuited or open-circuited line act like the imaginary part that we want. So that's what we're going to be working on in the next several set of slides.